for the do now, these 4 questions all relate to this information up here at the top. So within the multiple choice section of the AP test, we'll have what are called question sets. And so you want to make sure that you read, if it says, for example, this might say questions 1 through 4, refer to the information below. And so that means that you always want to come back to this information as you're answering those questions. So this is a mixture of NO2 and N2O4 is placed in a glass tube and allowed to reach equilibrium. So I'm going to underline equilibrium because then we know that this is an equilibrium problem. On the AP test, you can use pencils, pens, but you cannot have a highlighter. So you want to make sure if you take pens or pencils, whatever, you're underlining, circling, starring, things like that. And so number 1 says, if the pressure of N2O4 is 1.33 atm when the system is at equilibrium. So this is an equilibrium partial pressure. What is the pressure of NO2? So we're dealing again with equilibrium. Well, if you take a look up here, we have the equilibrium reaction and we have Kp. Well, if I write the Kp expression, just in general, how do we write an equilibrium constant expression? Products over reactants. Right? Only gases in aqueous solution. Since this is Kp, we're looking for the pressure of NO2. Well, because of that 2, it's going to be squared over the pressure of N2O4. There's our Kp expression. And so we have N2O4 at equilibrium. That means we can plug it right in. We also have Kp. Now remember, we do not get calculators on multiple choice. So what we're going to do is we're going to plug everything in. So we have the pressure of NO2 squared over 1.33. What is 3 times 1.33? 4, right? It's 3.99, so we'll round to 4. So 4 equals the pressure of NO2 squared. How do I solve for pressure? Square root. What's the square root of 4? 2. So the pressure of NO2 is 2. So we can do the math without a calculator. So 1 is B. Round where you can. So technically 3 times 1.33 is 3.99. Round your numbers. You can always round your numbers. Number 2, which of the following statements best helps to explain why the contents of the tube containing the equilibrium mixture turned a lighter color when the tube was placed into an ice bath? So we had something at equilibrium. The system was at equilibrium and we disrupted it. Thinking of Le Chatelier's principle. An ice bath means what is happening to the temperature? It's going down. Right? We're decreasing temperature. And remember, when we think about Le Chatelier's principle, we think about heat as a product or reactant. If we're decreasing temperature, that's like us removing heat. So it tells us when the tube was placed into an ice bath, it turned a lighter color. So when we decreased temperature, the reaction shifted toward the reactants. Well, if we removed heat, the reaction shifts in a way to create more heat. Remember, we're trying to undo the change that was made. So if it shifts to the left when temperature is decreased, it shifts to the left because we want to make more heat. And you can, if it's easier for you to just think about, put heat as a reactant, see what it would do, put heat as a product, see what it would do, you can do that. So if heat is a reactant, if heat is going into the system, what does that mean about that process? Endothermic. All right, the forward reaction. Forward reaction means this is your reactants. Now here's the thing with number 2. If you read the answer choices, even if you weren't sure whether it was exo or endothermic, you could actually cancel or eliminate C and D. Because remember, the only thing that changes activation energy is if you add what to a reaction? Catalyst. The only thing that changes, and a catalyst lowers the activation energy. Nothing's going to raise it. The only thing that changes activation energy is a catalyst. So then we know, okay, it's either looking for exo or endothermic. If heat is a reactant, it's endothermic. If heat is a product, it's exothermic. And it's telling us what happens when temperature decreases. Then number 3, which of the following best predicts how the partial pressures will be affected if a small amount of argon is added to the equilibrium mixture at constant volume? So there are 2 ways you can think about it. You can either look directly at the reaction and look at what adding argon would do, or look at Q. Right, you could look at Q, the pressure of NO2 squared over the pressure of N2O4. You're adding argon. Is argon in Q or is argon in the reaction? No, right, it's not there. Argon is a noble gas. It's an inert gas. It means it doesn't react. Adding argon is not going to do anything. Adding argon is not going to do anything. So when you add an inert gas to something at equilibrium, it's not going to do anything. And then number 4, which of the following statements about delta H for the reaction is correct? Well, looking at number 4, again, I know this is thermochem. We're doing this today, but just to tie this in. So it's asking about delta H. That's enthalpy. Remember, delta H tells us whether something is exo or endothermic. Well, in number 2, we already answered what type of reaction this is. We already said the reaction is endothermic. If a reaction is endothermic, that means delta H has to be positive because the system is gaining heat. It's gaining energy because it's going into the system. So I can eliminate A and B. Now, if you even just read the answer choices to C and D, we can actually eliminate the other incorrect answer. C says delta H is greater than 0 because energy is released when the bond breaks. If energy is released, what type of process is it? Exo. That doesn't actually match. This is endo, this is exo. That doesn't match. Correct answer is D. Delta H is greater than 0. Endothermic because the energy is required to break a bond. Energy is always required to break a bond. We'll talk more about that today when we talk about bond enthalpy. So again, these are actually 4 questions off of one of the practice tests. You can see how, although a lot of this was equilibrium, it still will pull in other topics as well. Any questions on the do now? Unit 6, just a general overview. We have exo and endothermic processes, energy diagrams, heat transfer. We'll talk about calorimetry using MC delta T. What happens when substances undergo phase changes. Then we look at delta H, different ways to calculate delta H. And finally, we'll end with Hess's law. So remember, thermochem was all about energy and heat. So how does the heat change in different processes? So before we actually get into topic 6.1, I just want to review some vocabulary. So as we're talking about thermochem and I say system or surroundings, right, you have an idea. So the system, that is our focus. The system is what we focus on. So if we're focusing on a reaction, the reactants and the products is our system. The surroundings is literally everything else. The container, the thermometer. If you touch something, your hand is the surroundings. So the surroundings is everything else. This is going to be one of the most important things. And this is when we get into solution calorimetry. This is one of the most commonly missed questions. When a solid dissolves in water, the thermometer that is being used is part of the surroundings. So when we're looking at a reaction or at a dissolution process, when a solid is dissolving in water, the thermometer that we use is part of the surroundings. So if the temperature is decreasing, that is the temperature of the surroundings decreasing, which means the system is absorbing energy. So then when we get into absorbing and releasing energy, we're going to talk more about endo and exothermic. That's part of topic 6.1. Endothermic, remember, we have heat flowing into the system from the surroundings. Or we can also think about it in terms of work. We're not going to get into work much because this is not a physics class, but work is done on the system. And I know that that has a different name. It's actually endergonic, but we can think about the same thing. Endothermic, right? Endo means into. So if it's endothermic, heat can flow into the system. Work can also be done on the system. You always are thinking energy is increasing, becoming positive. Exothermic, heat exits the system, goes from the system into the surroundings. So from the system. It's always about the system. And then in terms of work, work would be done by the system. That's why it's negative. Delta H is negative, or Q is negative for an exothermic process. Work would also be negative. It's losing energy. The system is losing energy. And then just in general, energy is the capacity to do work or transfer heat. And so E, energy, is work plus heat, or heat plus work, Q plus W. So the biggest thing here is thinking about the system, right? We always are focusing on the system. We're going to talk more about each and every one of these terms within topics themselves. The first law of thermodynamics is the law of conservation of energy. This means that energy is conserved. Right? Energy can change from one form to another, but it should not be lost. We can't lose energy just like we can't lose mass. Heat, when we talk about heat, we're looking at the energy that's related to temperature. We're going to talk much more about specific heat. Specific heat has its own topic with calorimetry. But specific heat is the amount of energy needed to raise the temperature of 1 gram by 1 degree Celsius. Every substance has its own unique specific heat. We can identify a metal through its specific heat. The larger the value of specific heat, the more energy the object can release or absorb before its temperature changes. Water's specific heat is 4.184. So it takes 4.184 joules to raise 1 gram of water by 1 degree Celsius. Metals have low specific heats, 0.37 joules per gram degree Celsius. That means it does not take nearly as much heat to raise the temperature. And then for objects with different specific heats, we would not expect the same temperature change. We have equal amounts. We put a hot metal into water, they're not going to change by the same temperature. They're going to transfer the same amount of heat, but they're not going to change by the same temperature. So now topic 6.1. This was all about endothermic and exothermic processes. So an endothermic process is when energy or heat is transferred into the system. Notice our focus is the system. An example of an endothermic process is an instant cold pack. So if you have an ice pack and you touch it, it feels cold because our hand, when we touch it, is part of the surroundings. The cold pack itself is the system. So then you have to think about, okay, if I'm touching it, my hand is the surroundings, what must be happening to the system if my hand feels cold? Well, the system is absorbing heat. It's absorbing heat from my hand. My hand is part of the surroundings. An exothermic process is when it exits the system. Right? Heat exits the system. That's why a hot pack feels warm. Again, our hand is part of the surrounding. So you're thinking, what is happening to the system in order for my hand to feel warm? Well, the system is releasing heat. Right? My hand feels warmer because it's releasing heat. Topic 6.2 gets into energy diagrams. And we talked about energy diagrams when we looked at kinetics because we talked about activation energy. So we looked at energy diagrams already when we looked at activation energy, but now we're focusing on the energy between reactants and products. So when we think about energy diagrams, something that is really important when we're looking at exo and endothermic processes is we're focusing on the bonds. When bonds are broken, that is an endothermic process. Breaking a bond is endothermic. So if I have a stick that acts as a bond and I try to break it, I have to put energy into the system. So breaking bonds is endothermic. Forming bonds. So forming bonds between atoms or forming attractions between ions is always exothermic. And so when we look at an energy diagram, we can actually look and see what has more energy, the reactants or the products. Well, if I take a look at these energy diagrams, so this side represents exothermic, the right side represents endothermic. Because you just ask yourself, okay, what has to happen to the reactants to get to where the products are? The y-axis is energy. So for the reactants to get to the products on this diagram on the left, reactants have to lose energy to get down to where the products are. That is an exothermic process. If the reactants are losing energy, energy is exiting the system, that represents an exothermic process. Right? Reactants lose energy. The other one, what has to happen for the reactants to get to products? Well, the reactants need to gain energy to get up to where the products are. Yes, it still has to overcome activation. But we're focusing on the difference between reactants and products. That's an endothermic process. So for topic 2, the biggest question here is if you were given an energy diagram, could you determine whether it is exothermic or endothermic by focusing on the difference between reactants and products? Topic 3 talks about heat transfer and thermal equilibrium. So when we talk about heat transfer, I was talking about this a little bit when I talked about specific heat. We're talking about what happens if two substances get put into the same container. Now, before we talk about this transfer, I want to review average kinetic energy. Remember, temperature is a measure of average kinetic energy. So if temperature increases, average kinetic energy increases. When we look at heat transfer is when heat flows from particles of a higher energy, warmer, higher temperature, to that of lower energy, which is a lower temperature. So heat transfer, the heat always goes from higher energy to lower energy. Heat transfer occurs when particles collide with one another. So it doesn't matter the state of matter, solid, liquid, or gas. When the particles collide with one another, heat will flow from higher to lower energy. Eventually, they reach thermal equilibrium, right? Thermal for heat means they have the same amount of heat, the same temperature. So two objects with different temperatures. An example is putting a sample of copper into a hot water bath, take it up to 100 degrees Celsius, and then we put it into a styrofoam cup with water at 20 degrees Celsius. This was the specific heat lab. Well, copper's at 100, water's at 20. Copper is at a higher energy, higher average kinetic energy because it was at a higher temperature, which means the energy is going to transfer from the copper into the water until they reach thermal equilibrium. So heat flows from the warmer object to the colder until thermal equilibrium is reached. So both substances have the same average kinetic energy. Heat, the amount of heat released by one object is equal to the amount of heat absorbed by the other. That is the first law of thermodynamics. So that means that the heat that copper lost, because it went from higher temperature to lower, so it's losing energy, the amount of energy, the heat that copper lost, is equal, but opposite in sign, to the heat that the water absorbed. Heat is Q, not delta T. The temperature changes will not be the same. What will be the same is Q. They change by the same amount of heat when they are added together. So this is just putting it, what we just talked about, into mathematical equations. So when heat is transferred between two substances, the heat lost by one is gained by the other. So this is thinking about system and surroundings, but we could also think about like copper and water. So negative Q, because energy was lost, is equal but opposite in sign to the heat that is gained. That is the first law of thermodynamics. A different way that you can represent the first law of thermodynamics is just by adding all of the Q's together. So Q of copper plus Q of water equals 0. That means all of the heats have to add up to equal 0 because energy has to be conserved. So no matter what, energy must be conserved. If not, something went wrong. There was some source of error. In calorimetry, typically our source of error is that if there's no lid or the lid isn't on tightly, some heat escaped. But assuming that we're in ideal conditions, energy is always conserved. So topic 4 looks at heat capacity and calorimetry. We're going to focus on the heat capacity side first, and then we'll look at calorimetry. So heat capacity. Heat capacity is looking at specific heat. So specific heat is, again, looking at the measure of the amount of heat that's required to raise 1 gram of a substance by 1 degree Celsius or 1 degree Kelvin. Always check your units for that. Now, with specific heat, although all heat transfer is equal, heat has to be conserved. Energy has to be conserved. Not all substances absorb or release the same amount of heat. No two substances, well, I shouldn't say no two. It's very unlikely that two substances have identical specific heats. Now, here's the biggest thing with specific heat. The lower the specific heat, the greater the temperature changes. This is why we use metal pans to cook. Because most metals have low specific heats. So their temperatures change to a larger extent more quickly. Copper's temperature changes a lot more quickly than water. And so when something has a low specific heat, its temperature will change to a greater degree. Now, here's another thing. Specific heat and molar heat capacity are not the same thing. Their units are different. Right? The difference between specific heat capacity and molar heat capacity is that specific heat is joules per gram degree Celsius. So how many joules does it take to heat 1 gram by 1 degree Celsius? Or 1 gram by 1 Kelvin? Molar heat capacity is joules per mole degree Celsius. It's just a quick molar mass conversion to go between specific heat and molar heat. So specific heat is just looking at how much energy does it take to heat a small amount of substance by 1 degree Celsius. Not all substances change by the same amount. Now going along with specific heat in topic 4 is calorimetry. So calorimetry, we did this coffee cup calorimetry where we had a coffee cup, we added water, we put some substance into it. It could have been a metal, maybe it was a reaction, and we used Q equals MC delta T. Q equals MC delta T, we're looking at the heat absorbed or given off by some process. We have mass, we have specific heat, and we have the change in temperature. This equation is on your equation sheet. Just pay attention to units. If C is given to you as molar heat capacity, if this is given as joules per mole degree Celsius, then make sure that you have moles and you have degrees Celsius. Delta T is final minus initial. And so again, this is still following the first law of thermodynamics. So if we have heat absorbed by water, that means it's being released by something else. We use a lid to prevent any heat loss, right? Keep everything in that calorimeter. Make sure the first law of thermodynamics is being fulfilled. Now going along with calorimetry, this equation again. This is on your equation sheet. Q is heat, either joules or kilojoules. Typically, we see Q in joules because specific heat is in joules. Pay attention to your units. On anything, not even MC delta T, on anything, just pay attention to your units. Delta T is always final minus initial. The delta in front of any variable is final minus initial. And then again, the first law of thermodynamics says that energy is conserved. So if heat is lost by one object, it's equal but opposite in sign to the heat gained by something else. This negative MC delta T equals MC delta T is using the idea that Q1 plus Q2 equals 0. And you could solve for any of these variables. You could solve for the mass, you could solve for the change in temperature, you could solve for the specific heat. Now, you don't need to write all of this. We already did a lot of this stuff already, but just to show you this process again, we're using this idea that Q system plus Q surroundings equals 0. Q1 plus Q2 equals 0. However you want to label it, Q metal plus Q water equals 0. And you can rearrange. You can plug in for MC delta T. Remember we did some work with a calorimeter constant. So if we had a calorimeter constant, that meant that the calorimeter actually absorbed some energy. And we just did C delta T for the calorimeter. Because the calorimeter constant is just joules per degree Celsius. Just pay attention to units. If there's no mass in your unit, you're not going to multiply by mass. It doesn't say anything about the calorimeter constant. We just use the idea that Q1 plus Q2 equals 0. Now, if we want to calculate delta H, that gets us into enthalpy. Right? Calorimetry, we focused on Q. We focused on heat. That was just in joules. Now, we looked at the coffee cup calorimeter. We did at least two labs with this, where we use the idea, right, that Q1 plus Q2 equals 0. Now, we're going to talk more about this, delta H, at the end, or in a different topic. But remember that Q is just joules. Q is just joules. Delta H is when we get into adding in the per mole. So topic 5 looks at energy of phase changes. So you need to make sure that you can identify whether a phase change is exothermic or endothermic. So in order for a solid to go to a liquid or a liquid to go to a gas, we have to speed up the particles. Solid, they're close together, right? They're just vibrating in place. Gas, they're moving all over the place. They have more energy. And so to go from solid to liquid and liquid to gas, energy has to go into the system. If you're speeding up the molecules, you need to increase the energy. When we think about phase changes, the energy that is going into the system to speed up the molecules, to make them move faster, to spread them out, is being used to overcome intermolecular forces. So going from solid to liquid, liquid to gas, those are endothermic processes. An example of an endothermic process is sweating. Sweating is the evaporation of water. Right? You're running and it's 85 degrees outside. You start sweating. Sweating is one way to cool your body down because as the water evaporates, it's endothermic. The sweat is the system. Your body is the surroundings. So as the sweat evaporates, it's endothermic. It's absorbing some energy from our body in order to evaporate. This shows a heating curve. So remember we talked about heating curves. With heating curves, remember if there is a slope, temperature is changing. The energy that's going into the system is being used to speed up the particles. So when there is a slope, that's when we use Q equals MC delta T. So we use MC delta T if we want to solve for Q when there's a slope because there's a temperature change. When it plateaus, when it remains constant, that is a phase change. There is no temperature change. What's happening is the energy that is going into the system is being used to overcome intermolecular forces. That's actually why we see a longer plateau during the evaporation period because all intermolecular forces are being overcome. Now, if this were flipped, if it were cooling down, that's exothermic. Because if it's cooling down, energy is being released. So if we're going from gas to liquid to solid, that's an exothermic process. Heat is being released to lower the temperature and to slow the particles down. And so what I have on the next slide is actually a sample question that we've seen quite often. When you're given this heating curve. And we looked at calculating heating curves. Remember, we did MC delta T for P, R, and T, and we did M delta H for Q and S. Right, M delta H. Delta H is the heat of either fusion or vaporization. So this question, during line segment Q, the substance is changing from a solid to a liquid. Only some, but not all of the intermolecular forces are broken. So a question that we see a lot is, we see why is segment S so much longer than segment Q? We see this on multiple choice a lot. Why is segment S so long, but segment Q is so short? And it's because segment Q, only some intermolecular forces are being broken or being overcome. During segment S, to get from a liquid to a gas, every intermolecular force needs to be broken, needs to be overcome. It's going to take more energy to overcome every intermolecular force, which is why we see a larger line segment. It takes more energy to overcome all intermolecular forces. We're talking about London dispersion, dipole-dipole, hydrogen bonding. Remember, intermolecular forces are overcome, not intra. We do not break covalent bonds during these heating curves. These heating curves represent phase changes. So this shows, again, what we use at each point on this heating curve. And so if temperature is changing, we use MC delta T. When temperature is changing, so we're just speeding up particles, we use MC delta T. If we are trying to calculate the amount of heat needed during a phase change, that is M times delta H. The delta H is either fusion for melting or vaporization for boiling. Now they will give us, if we had to do a calculation with a heating curve, they would give us specific heat capacities. they would give us delta H values. We would just need to know that we use MC delta T when there's a slope, because there's a temperature change, and we use M delta H during a plateau. And heating curves, right? This is endothermic, heat is being absorbed. If it's cooling down, that means that heat is being released. You can go back onto these slides if you need to refer to any of these, but this is when we're looking at calculating Q. Now, topic 6 introduces us to enthalpy. Enthalpy is delta H. So these are very, very important, and I didn't know where to put them, so I put them on this slide before we kind of dove into more delta H. So just like Q, we can look at the sign to figure out if something is exo or endothermic. Endothermic has a positive Q and a positive delta H because the heat is increasing. Heat is going into the system. If it's exothermic, delta H is negative, just like Q is negative because heat is exiting the system. Now, if the question asks you to calculate Q, they want to know the magnitude of heat. They want to know joules or kilojoules. Now, they don't necessarily ask for the sign, but Q is based on a certain mass. If you change the mass of something, you actually change Q. So Q is an extensive property. It changes based on the amount. Q is MC delta T. Give your units in joules or kilojoules. Now, if they want you to calculate delta H is an intensive property. Delta H is the ratio of heat to moles. And so if you want to calculate delta H is derived from Q. Q is joules or kilojoules. Delta H is kilojoules per mole of something. So to calculate delta H, we use Q, but we divide by our number of moles of substance. So delta H, our units are either kilojoules per mole or kilojoules per mole of reaction. We see that reaction down there. That means that if the reaction ran one time, this is the amount of heat that is absorbed or released. So there is a difference between Q and delta H. Q is just joules or kilojoules. Delta H is going to be the kilojoules per mole of substance reactant. So delta H gives us the amount of heat released or absorbed by a chemical reaction. This is thermochemical equations. So if we have this balanced equation here, here's the delta H value. Notice this per mole of reaction. What that means is 802 kilojoules of heat is released when 1 mole of CH4 burns, or 2 moles of O2 are used, or 1 mole of CO2 is produced, or 2 moles of H2O are produced. So this per mole of reactions, if the reaction ran one time, it's based on these coefficients. We can use this instead of a mole ratio, we use this with the moles to be able to go between moles and kilojoules. So you always just want to pay attention to your balanced equation. And then if you have limiting reactants, right, that ties into stoichiometry. So we'll take a quick break, use the restroom if you need to. We're almost done with Unit 6, actually, and then Unit 9 is going to be shorter.
Well, I gotta run the car now.
So going on along with enthalpy, so topic 6 just looked at delta H in general. So delta H is kilojoules per mole of reaction, and we can use balanced equations to help us with stoichiometry with heat. Now, topic 7 is bond enthalpy. So bond enthalpy is the energy required to break a bond, or the energy released when a bond is formed. Breaking bonds is always endothermic. Forming bonds is always exothermic, no matter what. If you want to break a bond, it's always endothermic. You have to put energy in. If something is formed, it releases energy. Now, when we're thinking about overall, the overall enthalpy of reaction, we can determine information about bond enthalpies based on the overall reaction. So if the overall reaction is exothermic, that means that the formation of bonds released more energy than the energy needed to break the bonds. Right? Think about it like a balance. If delta H is 0, that means that they were equal. But if the energy released is greater than the energy required, the overall reaction is exothermic. And we think about it the other way. The energy required is greater than energy released, then the reaction is endothermic. Now, when we're thinking about the strength of bonds, the amount of energy required, we can go back to this graph that we looked at before. Bond strength is determined by the distance between atoms and bond order. So bond order is the number of bonds between two atoms. If it's a single bond, bond order is 1. If it's a double bond, bond order is 2. If it's a triple bond, bond order is 3. Well, a triple bond has 6 electrons between it. It's going to be a lot harder for you to break a triple bond. Imagine if I was using a ruler as a bond, right? Using one ruler as a single, 2 as a double, and 3 as a triple. Don't actually bend them. All right, so one of them. This would be fairly easy to break. Single bond, fairly easy to break. Add another one. 2 gets more difficult. Well, if I have 3 rulers, right, a triple bond, this takes a lot more energy to break. So triple bonds are stronger than double and single. And so that actually helps us look at endothermic and exothermic. If the bond energy is greater, so a triple bond takes more energy to break, but it also releases more energy when it's formed. So the bond energy is positive if you're breaking it, but negative if you're forming it. So if we take a look at this picture of bond enthalpy, right? So here are our reactants. And then to get to products, we have to break each and every one of these bonds. So I'm breaking 4 CH bonds. I'm breaking 2 double bonds, right? 2 double bonds between O2. And then, so that takes energy. To break all of these bonds, it takes energy. But then when I make new bonds, it releases energy. The difference between these gives us the delta H. So to calculate delta H, it's right here. This equation is not on your equation sheet. To calculate delta H of reaction using bonds is its bonds broken minus bonds formed. You look on your equation sheet, you have a lot of other delta H, delta S, but you do not have this one. To calculate delta H of reaction when you're dealing with bond energies or bond enthalpies, and you know you're going to use this when you see a table that says bond enthalpy, is it's your number of bonds broken minus your number of bonds formed. Don't forget to take into account how many bonds you're actually breaking. Drawing the Lewis structures is going to be extremely important because you need to know that you're breaking 4 CH bonds and 2 OO double bonds. And you need to know how many bonds you're forming. So when you're looking at delta H using bond enthalpy, it's bonds broken minus bonds formed. Now, another way that we can calculate delta H is through enthalpy of formation. This is on your equation sheet. On your equation sheet, you have delta H equals the sum of the heat of formation of products minus the sum of heat of formation of reactants. Again, you're going to know what you have to use because they will have to give you heats of formation, either in a table or they're going to have to give it to you in the problem. This is when we were using Appendix C for all of our heats of formation. They will give you something like this on the test. Now, the standard enthalpy of formation, delta HF, is the enthalpy of formation of 1 mole of a substance from its elements. So here's an example. The heat of formation of CO is forming 1 mole of CO from its elements. So it looks a little bit weird because it's 1/2 O2. But it needs to be 1/2 O2 because the definition of heat of formation is when you form 1 mole of something. You form 1 mole of something from its elements. When you're using heats of formation, pay attention to states of matter. Because you'll notice here, gaseous water and liquid water have different delta H values. So just pay attention to states of matter. And then if you remember, elements in their standard states do not have heat of formations because they don't have to form. They're already in their most simple state. O2 gas, iron, sodium, solid carbon, Cl2 gas. Elements in their most stable state do not have delta HF values because they do not form from their elements. They're already in their most standard form. So this is another way that we calculate delta H. Now, this table is just summarizing what we just talked about. So I just wanted to put a summary slide, so if you needed to go back and refer to it, you could. So this is looking at bonds broken minus bonds formed. So remember, bonds broken are always endothermic, bonds formed are exothermic. You always do broken minus formed. Don't forget about Lewis structures when you're looking at this. And then if you want to calculate delta H of reaction and you're given enthalpies of formation, that equation is on your equation sheet. And then this is looking at what happens if it's exothermic. That means you're releasing energy. If it's endothermic, there's an absorption of energy. So when it's endothermic, that means that you have to put more energy in than what you're getting out. So that means you're trying to break stronger bonds. You're forming weaker bonds. And then the last topic in thermochem is Hess's law. So remember, Hess's law is if we add 2 or more reactions together, we have to manipulate delta H in a way, and then we add the 2 together. So if we flip a reaction, we flip the sign of delta H. We multiply a reaction by 2, we multiply delta H by 2. We add the reactions together, we add up our delta H values. So Hess's law uses what we learned initially. Change the sign, multiply by 2. Remember, equilibrium constants are different, but delta H, delta G, and delta S all use Hess's law, where we flip the sign, add them up, and then we can figure out if something is exo or endothermic. Any questions on Unit 6 before we flip over to 9?
I have one back on 6.6, I think. Wait. Next page. Wait. One before that. Yes, that one. There was a question on the diagnostics one that we did about this. It was like, when does their bonds form, I think?
Yeah. So you're talking about looking at this diagram.
Yeah.
So when we look at this diagram of energy versus distance, really, this helps us to see when the most stable bond is formed. And the most stable bond is formed when the attractive and repulsive forces are balanced. So that is at the lowest point here. So this actually, the distance that's on the x-axis, tells us the bond length. And then the energy, so this is actually the bond energy. So it says negative 436. That means if we formed this bond, it would release 436 kilojoules of heat. Now, if we broke the bond, right, this would just be positive because it's endothermic. But when you're looking at a diagram like this, it always tells us 2 things. It tells us bond distance, so that's this picometers, and it tells us bond energy. And so the lower down the peak would be, the lower the energy would be, which means the more energy it takes to break, or the more energy that's released when it's formed. Or like the further over this way you are, the closer it is. So like a triple bond, we would expect the bond to be shorter. So we would actually expect a triple bond, right? The peak would kind of be down over here.